Hello chemists, this is Ms. Pluchino and you are watching Screencast 3.2 on periodic trends. In the previous lesson we discussed the layout of the periodic table and how it's currently organized. We know it's arranged in order of increasing atomic number. It turns out when you arrange the elements in order of increasing atomic number, you see some trends or patterns that are going to come up as you move across the table from left to right and from top to bottom. Two of these trends are atomic radius and first ionization energy, and those are the ones we're going to focus on today. If we look at the do now, it says atomic radius and first ionization energy have an inverse relationship. You might have noticed that from your reading. Explain why this is observed. So pause the video, come up with a brief explanation. So if you weren't 100% sure how to explain that, or even as you were reading it, you were a little bit confused, that's okay. We'll get you straightened out during this lesson. What I'd like you to think about, though, kind of in the meantime, let's say that you're holding on to like a pencil or something, and one of your friends says, I'm going to come and take that from you, and you don't want him or her to steal it from you. Think about how you're going to hold that pencil to really kind of maximize your strength and make it as difficult as possible for the other person to take it away from you. And that's a pretty decent way of thinking about atomic radius and first ionization energy. So let's get into these trends. We'll start with atomic radius as, in my opinion, it really drives every other trend that we're going to talk about. Hopefully, just based on the name, it's kind of a dead giveaway of what this is. We're talking about the radius of an atom, or in other words, we're looking at size. Here's the technical definition: 1/2 the distance between the nuclei of identically bonded atoms. So we have two atoms exactly the same, atom X. We've got their nucleus at the center. We're going to bond them. Then we're going to measure the distance and divide it in half, and sure enough, we get the radius, just like you would in math class. I guess they usually use lowercase r. This distance is measured in picometers, which hopefully, as you would imagine, is a very, very small unit. It's even smaller than nanometers. It's 10 to the negative 12 meters. And when you think about it, this makes sense. We're measuring something the size of atoms, actually half the size of an atom. So we're going to need a really, really small unit to work with. Different elements are going to have different atomic radii, and we're just going to have to really focus in on not knowing what their individual radius might be, but understanding what happens to the size of atoms as we move across the periodic table and down the periodic table. Using the notes that you took from the reading, you should be able to determine what the trend is as we go down a group in the periodic table. So if you look at the little periodic table, it's going down, and what the trend is as you go across the period. That's directly out of the notes. Explaining why this observed is a little bit more complicated. So if you haven't done so already, pause the video, think about it, see if you can come up with reasonable explanations for both, and then we'll talk. As you go down a group, so as you start at like period 1 and you work your way down to period 7, the general trend is that atomic radius increases. This one is usually fairly straightforward for students to understand. Let's think about group 1, our alkali metals. We've got hydrogen, so it's nucleus, 1 energy level. We've got lithium, nucleus, 2 energy levels, and you know what, maybe I'll draw those going down so it makes a little bit more sense visually. Then you've got sodium, 1, 2, 3 energy levels. Below sodium is potassium, 1, 2, 3, 4 energy levels, so on and so forth, all the way down to francium. So hopefully that makes sense when you think about it. Every time you drop down to a new row, you're adding a whole extra energy level or orbit. And the more orbits you have, the larger the atom is going to be. Explaining the trend that we see moving across the period from left to right is a little bit more involved. So I'm just going to get this erased and out of the way. We can talk about it. From the reading, hopefully you found that as you go from left to right across the periodic table, atoms tend to get smaller and smaller. So the trend is that we see atomic radius will decrease as you go from left to right across the table. I want to think about period 2. So we've got lithium, beryllium, boron, carbon, so on and so forth. With lithium, I've got my nucleus, and I've got those 2 energy levels, and I've got the electron configuration 2-1. Next door, I have beryllium. Same thing, 2 energy levels, 2-2. we'll do boron, 2 energy levels, 2-3, and why not, we'll do one more just for good measure, carbon, 2 energy levels, 2-4. At first glance, it might be really difficult to understand why the atoms get smaller and smaller as you move across the periodic table. You've got the same number of energy levels present, just 2 of them, so it's not the same driving factor that it is for why atoms get bigger down the group. What about this could possibly make the atoms get smaller? And you need to think about the nucleus. Inside the lithium nucleus, we have a total of 3 protons, so we've got a charge of +3. Beryllium has 4 protons, so +4. Boron, +5, due to its 5 protons, and carbon, +6, due to 6 protons. So as we move across the periodic table from left to right, the strength of the nucleus is increasing. We're getting a more positive and therefore more attractive nucleus. So those electrons that are hanging out in the second energy level, they're going to be more drawn to a nucleus that is more positively charged. So the general trend that we'll see is that our group 1 elements should be the largest in that period, and then as you get down to the halogens and the noble gases, you should have very small atomic radii. And it all has to do with the fact that the nucleus becomes stronger, and since the electrons are going to go into the same energy level, in this case right here, they're all going into the second energy level, or the second orbit, that proton-powered nucleus is going to be better at pulling the electrons towards itself, and it will make the atom smaller. This graph is just giving you another way to look at our atomic radius trend. I know the axes are a little bit blurry, so just to clarify, across the x-axis it says atomic number, or number of protons, and on the y-axis we have atomic radius. I want to focus on periods 2 through period 6 and look at what they've got in common. In each case, the group 1 metal is the largest of everything in that period. We've got our group 18 nonmetal, a noble gas, is being, if not the smallest, definitely one of the smallest radii in that period. And the general trend is that things get smaller as you go from left to right. If you look for at top to bottom, whether you want to talk about the size of the group 1 or the group 18 elements, it's the same general trend. As you move down the group, going from lithium to sodium to potassium, or from helium to neon to argon, you see that continual increase in size, which is exactly what we talked about on the previous slide. Another way that you can explain the atomic radius trend is through something called effective nuclear charge. And effective nuclear charge is really all about how strongly does the electron feel the pull of the nucleus. So the net positive charge experienced by an electron in a multi-electron atom. Outside of hydrogen, every other atom on the periodic table is going to have multiple electrons, and those electrons are aware, so to speak, of the other electrons in the atom. So we've got our positively charged nucleus, it's kind of like golden yellow thing at the center of the atom. Our electron of interest is here, the little black dot. And in this green sphere, circle, we've got electrons that cancel some of the nuclear charge. In other words, they're kind of, you can almost think about it as absorbing some of that nuclear charge, or they're getting to experience the pull of the nucleus. And because the nucleus is attracting them, it's not able to attract our electron of interest quite as strongly. This is why when you add extra levels onto your atom, so as you go down the group and the electrons get farther and farther away, the nucleus just can't pull them quite as tightly as they can in smaller atoms. So the electrons that are closer to the nucleus tend to block the pull of the nucleus. They're kind of I guess hogging all that pull, you can think about it, and the ones that are farther away are effectively shielded from experiencing the full strength of the nucleus. No need to stress out about the exact definitions of effective nuclear charge. Like I said before, I just wanted to give you another way to think about atomic radius. The other trend we're going to cover today is first ionization energy. We know what the word ion means. Ions are atoms that have either lost or gained electrons, and as a result have a charge. In the case of first ionization energy, we're talking about the amount of energy that is required to remove the outermost electron. So in this case, an electron is being lost, and as a result, we form a cation, a positively charged ion. Regardless of whether you're working with a metal or a non-metal, removing the outermost electron or one of the valence electrons from an atom always requires energy. Usually you can just kind of pump enough energy into the atom where the electron becomes so excited, it's essentially just pulled away from the atom altogether and it's no longer attracted to that nucleus. So if we take a look at this picture of the atom, we've got our nucleus at the center, of course, and one of the outermost electrons, the valence electrons, is going to be pulled out of there, and that's what we're talking about ionization energy. How much energy do you need to provide to get one of those electrons to come off? So again, you read about this in your homework last night. See if you can explain the trend that's observed as we go from top to bottom down a group, and the trend that we observe as we move from left to right across the table. As you go from the top of the group down towards the bottom of the group, first ionization energy decreases. As we looked at atomic radius, we know that moving down the group, atoms tend to get larger and larger. So again, we'll just kind of quickly sketch that. And it doesn't really matter if you're thinking about a group 1 or group 2 or group 13, 14, 15, so on and so forth. We know that as you move down the group, the atoms get larger and larger. If you think about where that valence electron is, you can see that it's getting further and further away from the nucleus. Therefore, the nucleus, due to electron shielding, isn't going to be able to attract that electron quite as tightly or as strongly as that atom gets larger and larger. At the beginning of this lesson, I told you to think about it like if you're holding a pen and your friend says, I'm going to take it from you, how you're going to hold it to make it really difficult for them to take it away. And chances are you're going to keep that really close and tight to your body because that's how to prevent somebody from stealing it from you. And if you hold it way out, far away from your body, it's going to be really easy to take it away. It's the same idea with the electron. The smaller atoms hold their electrons very, very tightly and very close to the nucleus, so there's that strong attraction. And it's going to be more energy intensive to try to take away the valence electron. Now let's look at the trend as you go across the period from left to right. Again, from the notes, you should be able to figure out that we see an overall increase in first ionization as you move from left to right, regardless of what period you're in. Again, we can kind of think about this in terms of the atomic radius trend. We'll go back and look at period 2, where we've got lithium, we've got beryllium, we've got boron, carbon, we'll throw one more in there for good measure, nitrogen, and we know we've got like 2-1, 2-2, 2-3, 2-4, 2-5, and ultimately we have an ever increasingly strong nucleus based on the elements that are present. Let's just get these in there. Carbon, nitrogen. We know every time the nucleus gets stronger, the atom actually gets a little bit stronger so long as those valence electrons are in the same energy level, and in this case they're on the second energy level. So nitrogen is the smallest atom, and just like with the going down the group trend, we talked about atoms that hold their electrons closest to the nucleus are going to be more difficult to take the valence electrons away from. So something like nitrogen, which has a very strong, powerful, attractive nucleus at +7, is going to hold its 7 electrons closer to it, making it a smaller atom and therefore making it more difficult to try to take one of the valence electrons away. Just like with atomic radius, I'm going to show you a graph, another way to visualize the first ionization energy trend. As you would expect, the noble gases have the highest ionization energies. I'm going to circle those points on the graph. And the alkali metals, the group 1 metals, there's cesium and rubidium, have the lowest. And this is really what you would expect. As you go across a column, across the row, we can see that overall there's a general trend of first ionization energy increasing. And as you go down a group, so we can look at helium to neon to argon, so on and so forth, we see first ionization energy decreasing. So just another way to look at the trend. it is possible to perform second ionizations or third ionizations and continue to make cations that are more and more positive. And you had this in your textbook, and I just want to take a moment to talk about it again. So we've got the different ionizations. IE sub 1 stands for ionization, or first ionization, second ionization, so on and so forth. And you can see that you get to these like gigantic jumps. So I want to look at like starting with lithium, actually. It's 520 kilojoules per mole to get rid of the first electron. All of a sudden it jumps up to almost 7,300 kilojoules per mole to get rid of the second one. In beryllium, we see something kind of similar. 900 at not quite, but almost doubles to about 1,800, and then we see this huge jump again to about 15,000, and that kind of progresses down the line. We see this because of completed octets, and that's not something we've really talked about in great detail just yet. It is going to come up in a later lesson, but suffice it to say that really all of these elements, if you're going to remove electrons from them, I guess I can get all these guys too, even though they're not really covered in the table. If you start removing electrons, they're going to want to try to look like helium. It turns out that there is a stability associated with having a full outer shell, and once they have that, they're really hesitant to give it up. So if we think about lithium, it starts off at 2,1, it drops down to just 2 as its electron configuration, and then if you try to take that other one away so it no longer looks like helium, it's going to be very energy intensive. It's going to take a lot of energy. Beryllium starts off 2,2, goes down to 2,1, try to take away that third electron to get down to 2, and you see the same, to get from 2 down to 1, excuse me, and you see the same thing happening. So basically this is telling us that once an element has the same electron configuration as a noble gas, it's going to be really stubborn about giving up electrons. I'd like to finish up our lesson today by doing a couple of practice problems. So in your workbook, take a look at page 54, and I want to focus on practice problems 2, and we'll do A and B, and also take care of question 4, A and B again. So in the case of question 2, you're trying to order the elements from largest to smallest, and for 4, you're going from lowest to highest ionization energy. Pause the video, try these out, and we'll check them over together. So the key to answering both these questions is really using the periodic table and keeping the trends in mind. So let's start off with question 2. We want to order elements from largest to smallest. So one thing that you might find helpful, because some people have trouble remembering the trends, is once you've got your test paper, for example, just draw some arrows. When it comes to atomic radius, I know that I see things decreasing as we go across the table and increasing as we go down the table. You can think about it again in terms of the strength of the nucleus or the number of energy levels that are present, whatever you've got to do to really cement that idea in your mind. So for the case of question A, we've got xenon, neon, helium, and krypton. So I want to find those on the periodic table. And if you look at your periodic table, I guess I moved stuff around, you can see that they all fall into the noble gas category. They're all in the 18th column. As I go down a group, the size of the atom increases. So we're going to go from largest to smallest. The largest of all of these should be the one that's at the furthest at the bottom of group 18. So for us, that's going to be xenon. As I make my way up, the atom should get smaller and smaller. So xenon's taken care of. Okay, then I see krypton above that. Then I'll see neon. And finally, helium. Let's take a look at question B. You've got chlorine, magnesium, sulfur, and silicon. Again, find them on the periodic table. Magnesium, silicon, sulfur, chlorine. These are 4 elements that all fall in the 3rd period. So again, atomic radius, as we go across the periodic table, things, I should say the atoms get smaller and smaller due to a stronger nucleus. So my largest is going to be the one that's furthest to the left, the most metallic. So that's going to be magnesium. As I make my way across period 2, I'd get to silicon, and then sulfur, and then finally chlorine. Things are a little bit more involved in questions C and D. Try them out on your own and check the answer key on the course website. Let's move over to talking about ionization energy. Same idea. If I go ionization energy, I'll draw my little picture just to remind myself. As I go across, we're going to see it increasing, and down it decreases. It is the exact opposite of the atomic radius trend. So I want to order the elements from lowest to highest ionization energy. So I want to start off with the metals and hopefully end up with the non-metals. Or start at the top of the group and work my way to the bottom. Oh, I said that opposite. Start at the bottom of the group, that's going to have the lowest, and work your way up to the top. So we have chlorine, fluorine, iodine, and bromine in question 4A. Find them on the periodic table. They're all group 17 nonmetals. The lowest ionization energy is going to be the one that is lowest on the table. So that is going to be iodine in this case. As I work my way up the table, I'd get to bromine. Then I've got chlorine. And finally fluorine. So the lowest one, again, is the one that is at the bottom of that group, as ionization energy decreases as you go down, and the highest one is going to be at the top of that group, in this case fluorine. Question 4B, fluorine, beryllium, carbon, and nitrogen. Find them on the periodic table. Hopefully you notice they're all in period 2. The lowest ionization energy is going to be the one farthest to the left. So in this case, it will be beryllium. As we make our way right across the periodic table, we'd run into carbon first, then nitrogen, and finally fluorine. That would have our highest ionization energy in this group. Again, I would suggest taking care of practice problems for C and D and checking your work. Questions like this often seem really simple and straightforward to students, but they really struggle when it comes down to the test. So make sure that you know your trends. Make sure that you understand how atomic radius and ionization energy change in terms of do they increase or decrease as we go down a group and across a period, and also be able to explain why we observe that happening. Keep on practicing, and I will talk to you soon.